Ajay Kar is still in your department or he retired?
Sorry?
Ajay Kar, there used to be Ajay Kar in your department.
Yes.
Has he retired or is still there?
He retired just a couple of years ago, a year ago or so.
The question
Yeah.
and answer. Just
He
neither is
mentioned,
over.
you when I met him.
Okay, I see. Okay.
COVID is here in Rochester right now.
Yeah.
So I'm in person, and he's almost in person. One of the two of us. Oh, no, I want. Grab my slide. See, there's no waste in the cookies because they're cellophane. So the ones that don't exist, we can
Anyway,
They freezes. They get fall nicely.
他 list 在那边一半人在那，过去第一件事就是三八的，他在三现在是不是，再把东西上去，一会儿回来再问。你不要非常超，我操，这人确实。哎，刚画条线，他骂别人3次。Good fish.
Bob, there's too much noise on the channel there.
OK， 好，这样就是说，你给我提意见的时候，你有想过你做的更好？我跟同学效果这个好，挺好，挺好。天天在发着。
I think we should get started. If you want to introduce now, go ahead.
你先坐下。
In about 2 minutes.
他问，
Whether you
Maybe,
can hear me or not.
yes.
did you work on structured light as an undergraduate?
Actually, funnily enough, I did not. I worked on entanglement, but I did not work on structure. People work on structure.
Okay, but you worked on quantum technologies as an undergraduate. I'm gonna tell a good story about this.
他说 Angela Musk， 我跟他说你这 Angela Musk 跟妈有个故事。Angela Musk 帮他干嘛？
All right, everyone, we're gonna get started.
Okay, Bob, go ahead.
So it's my great pleasure to introduce our speaker for this week. It's Professor Mehul Malik from Harriet Watt University in Scotland, in the UK. Scots are very proud of their nationality. So they usually say they're from Scotland, not from the UK. But that's an aside for right now. Mehul did his undergraduate work at Colgate University. He then did his PhD at Rochester as part of my group. And he then moved on to Anton Zeiliger's group in Vienna before taking his position in the UK. Now, in the time after Mehul had left Vienna, one of his 2 mentors won the Nobel Prize, and it was not me. We're happy for Zeiliger. He certainly deserved it. As an undergraduate, Mehul did a double major, a major in physics and a minor in art and art history. And I can tell you from personal experience what a great artist he is. For several years, I had a Malik original hanging in my living room. So he is a Renaissance man, you might say. He going to talk to us today about harnessing structured light for quantum networks of tomorrow. And please help me to welcome him.
Okay, thank you very much, Bob, for that very nice introduction. It's a great pleasure to be with you guys virtually. I wish I was there in person, although I heard there's a snowstorm on the horizon, so I'm not particularly sad about missing that. Right, so I work at Heriot-Watt, as Bob pointed out, and I've been here about 5 years, and I'm going to try and give you an overview of many different things that my group works on. So let me get started. So my group is called the BBQ Lab, which stands for Beyond Binary Quantum Information. We are located in Edinburgh, which is up here in Scotland. And the city is, of course, beautiful. It's got an amazing atmosphere. And we're located a bit outside the city, which means that we have lots of space for labs and the likes. Right, so here's a rough outline of my talk. So I'll start with an introduction to the field of high-dimensional quantum technologies, and then I'll talk about 3 different things. One, how we generate high-dimensional entanglement in my lab. Second, how we transport it through multimode fibers. And finally, I'll tell you about a recent result from my lab where we developed a new way to manipulate high-dimensional quantum states of light. So let me start by talking about something you're probably all familiar with somewhat, is the second revolution. Now, you may have heard this phrase mentioned in the media, but this is really a revolution built around the control and engineering of individual quantum systems, and relies on uniquely quantum effects such as superposition and entanglement. So on this slide, I've thrown up some examples that make us realize that we really are in the middle of a quantum revolution, so to speak. And things like the Chinese quantum satellite that's beamed down entangled photons from space, Google's 72-qubit, and I should probably mention more recent results by IBM on a few 100-qubit quantum processors. And here, maybe you can even read the fine print that says, squeezed light would lead to daily gravitational wave detection. So squeezing has been incorporated into LIGO for enhancing the sensitivity of gravitational wave detection. And of course, there's plenty of excitement around quantum funding. And there's national programs in the US now. The UK's national program has been going on for almost 9 years now. So there's a lot of momentum being built around quantum research in the world for good reasons. So what is the role of photons in all of this? Photons are really the ideal carriers of quantum information. There are many, many physical platforms that are in the running for the quantum computer, and we don't know which one is going to be the first, let's say. But photons are really the only quantum particle that you would really want to encode information on and send it across a channel. Right? This is because they are fast, right? They travel the speed of light and they're cheap. They don't interact much with the environment, which is plus and a minus, and they can be efficiently transported through waveguides such as optical fibers. Above everything else, we are really building on a massive classical photonics industry and research backbone. And the U of R and the Institute of Optics, of course, has played a significant role in this backbone, building this backbone. Right. So that brings me to photonic quantum technologies and our ability to encode quantum information, qubits, so to speak, which are quantum versions of bits on a single particle of light, has really led to a revolution in how we process and store and transport information, right? So the field of quantum cryptography allows us to have unconditional security based purely on the laws of physics, and future networks of interconnected quantum computers are expected to really change the way how we process and use information. However, qubits are inherently limited in how much information they can carry, which is a bit. And a quantum network built upon qubits will not be able to keep up with the data demands of our global society. And the other slightly subtle reason is that qubits are very susceptible to noise and loss, and they are very quickly, we lose quantum effects such as entanglement when you have a photonic qubit traveling through a noisy environment. So then the question naturally arises, how then do we reach this vision of a global quantum network or a quantum internet, so to speak? So the emerging field of high dimensional quantum information poses one possible solution. One can encode many bits on a single particle of light by using its spatial structure or its frequency and time information content. And this is not a new concept. So if we look to the classical comms field, we look at the past 20 years in classical comms, we'll find that huge jumps in data rates have been achieved by the use of wavelength and space division multiplexing, which we all use today, in fact. And then the future is expected to lead to even faster, just stunning data rates through the use of SDM in particular. If we plot on the same graph the highest data rates, secure key quantum data rates that have been achieved, you will see that similar jumps have been achieved through the use of time frequency encoding, and one can expect similar jumps in quantum data rates to be achieved through the use of positional momentum encoding, or what I call XP here. So this other slightly subtle advantage of high dimensional quantum states of light is that they are more robust to noise. They can tolerate much more noise until we lose quantum properties such as entanglement, and I'll tell you a little bit more about that later. Applications aside, there's also very interesting fundamental concepts that one can explore with the high dimensional quantum states, and one of which is high dimensional entanglement. You can have entanglement or entangled photons that are entangled in their transverse spatial degree of freedom. You may have heard of orbital angular momentum modes or twisted light, as it's called. And you can have entanglement in this degree of freedom, which was incidentally shown by Anton Zeilinger way back in 2001. You can have entanglement in the time of arrival or time bin degree of freedom, and as well as the conjugate frequency degree of freedom. And then when you go to high dimensional entanglement, you get access to these very interesting exotic entangled states where each particle can be living in a Hilbert space with a different dimension. So here I'm showing you an example of an entangled state that I created during my postdoc time in Anton's group, where each particle lived in, two particles, entangled particles were living in a three-dimensional space, and one lived in a two-dimensional space. So we call this a 3-3-2 type of entanglement. Just a quick ad, if you're interested in reading more about these different types of platforms for high-dimensional entanglement and methods to certify them, I direct you to this paper on a review paper that I've authored with some of my colleagues. Right, so this brings me to the generation of high-dimensional entanglement. How do we generate these states in the lab? Let me start with polarization entanglement, which some of you may be familiar with. So you can have two photons that are entangled in their polarization, and this is described by this equation here, which is particle 1, particle 2. And if you find one particle to be horizontally polarized, you know immediately that its partner is horizontally polarized, and so on and so forth. Now, if you do a basis rotation, in this case, we could literally physically rotate our experimental apparatus by 45 degrees, you would find that the state is also perfectly correlated in the diagonal anti-diagonal basis here, right? And this is, you can verify this by doing some simple maths, by substituting these equations in here, and you'd find that, again, if you made measurements in the DA basis, as we call it, you'd find that it's perfectly correlated. This is really the signature of entanglement: correlations in conjugate observables, complementary properties, such as time frequency, position momentum. In this case, we're talking about a discrete system, so it's two different bases, conjugate bases of polarization. In the lab, we create entangled photons using nonlinear processes. Here I'm showing you some nonlinear bulk crystals, BBO crystals, and in these types of systems, you have processes such as spontaneous parametric down conversion taking place, where one higher energy photon, blue photon here, is absorbed, and two lower energy photons, red here, are emitted. So let's look at this process a bit more in detail, right? So this is what a schematic looks like, showing the two photons that are emerging. And here I'm showing you the two photons are referred to as a signal and an idler. And the state that describes these two photons in the momentum degree of freedom is given by this equation here, which we call the joint transverse momentum amplitude, or the JTMA. And this is a four-dimensional function, but in fact, it's fairly straightforward. It's made up of a strongly anti-correlated sinc part and a correlated Gaussian part here, right? And so if I plot this this function in one dimension, so in the y-axis for one photon and y-axis for the other photon, I find that the function has this structure here, right? And it's described by two parameters. One is one of which is sigma s, which is the width of the size of the correlation, and sigma p, which is the strength of the correlation. And both of these parameters are related, strongly related to various aspects of my setup. For example, the strength of correlation sigma p is inversely proportional to the size of my pump beam. So if I pump with a very big pump beam, I'll generate a pair of photons that has a large distribution of momenta, the other way around, a very tightly correlated momenta. And then sigma s is related to the length of the crystal as well as the pump wave vector in the crystal. So what the takeaway message from this slide is that I can engineer highly entangled pairs of photons by judicious choice of how I pump a nonlinear crystal, and how and the crystal properties, of course, themselves, as well as the length of the crystal, and so on and so forth. We recently published a paper where we described a full theoretical model for SPDC in the spatial degree of freedom, and we also demonstrate a very simple way to measure this JTMA, and I'll refer you to that for more details. Right, so ideally, if we have a high dimensionally position momentum entangled state, we'd like to measure it. And in an ideal world, I'd have access to single photon cameras that I can then correlate and reconstruct my two photon wave function that would look probably something like this, where all of these specific modes are referring to pixels on my camera. However, in reality, cameras such as this don't yet exist for single photons, or at least not of a very high quality. So what we revert to in the lab is single detectors. So we have single detectors that function very well for measuring single photons. And then we use holograms to essentially scan through any basis of interest. So these holograms are implemented on devices known as spatial light modulators, which I won't talk too much more in detail about. But what I will say is that once we know the joint transverse momentum amplitude here, we can use this information to then very carefully construct spatial mode bases that allow us to maximize the correlations and really engineer any types of entangled states that we want. So as one example, here I'm showing you two holograms that we've programmed on our holographic devices. And then we can scan through all of our macro pixels. And what this will do is give me some data, two photon anti-correlation data, where one party known as Alice here, the other party known as Bob are measuring particles, measuring photon counts, and then seeing that they indeed have very strong anti-correlations in pixel. So in this case, it's a macro pixel basis. Now, this is not enough to certify entanglement. As I showed you earlier, entanglement, a property of entanglement is that entangled states are strongly correlated in conjugate or complementary properties. So for this, we really need to certify that the state is indeed strongly correlated in another basis, right? So this brings me to a fundamental concept that is central to a lot of the work that I'm going to talk about today, which is that of mutually unbiased bases or modes. So this is a high dimensional generalization of this two-dim polarization basis that I was talking about earlier, horizontal, vertical, diagonal, anti-diagonal. But so let's take a three-dimensional basis made up of macropixel nodes 0, 1, and 2. So using this recipe that was laid out in this paper by Bill Wooters and Fields, one can construct multiple bases. So for prime dimension D, you can have D plus 1 bases. So in this case, we have 4 possible bases. The first one is just a discrete Fourier transform, right? Where you just add up the 0, 1, 2 with specific phases between them. And then you can construct 2 more bases, right? So this is a standard recipe. The main point is that states within a basis are orthogonal. States across bases have a defined overlap that is related to the dimension of the basis. Now, the beautiful thing about holographic measurements is that we can use them to really measure any coherent superposition of states. So here, what I can do, instead of scanning through my macropixel space by individually turning on and off pixels, I can modulate the relative phase of these pixels in any possible way I want, of course, limited by some resolution of the device. But for a 31-dimensional pixel space, I can construct 32 possible MUBs. And then, so let's pick one of those MUBs, right? And so this is actual data from the lab where I scanned through a second basis and found that I have very strong anti-correlations also in my second MUB, right? And so using these 2 sets of data, I can then apply some formulas that allow me to lower bound the entanglement dimensionality of my state. So I won't go into detail here, but essentially what we can show is using any 2 mutually unbiased bases, we develop some theoretical tools to say that this state is indeed entangled in 3 dimensions, but not 4, let's say, and so on and so forth. Right. So in some recent work, we extended this idea to a technique that allows us to certify entanglement very quickly. So in this case, I'm showing you 19-dimensional pixel basis. So these are 20 mutually unbiased bases. So we've measured correlations in all 20 MUBs, and we were able to show very high quality entanglement for the spatial degree of freedom, which was fidelity of 94%. And we were able to do it very, very quickly, which was enabled by the theoretical tools that we developed. Even more so, we tried to push the dimensionality of our 2-photon entangled state, and we were able to show 55-dimensional entanglement in a 97-pixel MUB, right? So you might find that this looks a bit familiar. This is no coincidence. So multi-core fibers have a transverse mode profile that looks quite like these macropixels. So the goal of working with these pixel bases is that we want to be able to interface them with an actual communications infrastructure. I promised you noise robustness, and so very briefly, I want to tell you about a result where we showed that high dimensional entanglement can indeed tolerate a lot more noise and a lot more loss than qubit entanglement. So this is a scenario in which entanglement is being used to securely transport information, in this case, a key. And when you use entanglement, you can have a scenario where your measuring device, your channel, as well as your source can be completely untrusted. You can still certify still have security. This is known as a one-sided device independence scenario. And it's the most, I would say, device independence is the most secure form of quantum communication that you can possibly have. So what we showed was that by increasing the number of measurements involved in our experiment, and in fact in our state, we can tolerate increasing amounts of loss as well as increasing amounts of noise. So this dotted line here is the best you can do with qubits in the limit of infinite measurements. And you see you can never beat 50% white noise. What we showed was by using just 53-dimensional states, you can reach fairly extreme regimes of loss and noise. And so here's some experimental data where the pink region, we cannot certify any entanglement. This corresponds to this regime here with about 78% noise and 94% loss. And then when I increase my dimensions from 23 to 41, we find that we are able to certify entanglement, not only certify entanglement, but also do it very quickly, drop the time by 2 orders of magnitude, which was kind of a surprise actually. So that brings me to the second part of my talk, which is on the transport of high dimensional entanglement. Just trying to keep track of my time here. Right. So today I'm going to talk about how we transport entanglement through complex scattering media. Now, why complex scattering media? Well, complex media all around us, right? From the foggy weather, clouds, to skin, and interestingly, a multimode fiber is also a type of a complex medium where light going in comes out looking like this, right? So if you send light into a multimode fiber, the modes mix coherently, and you get something, get a speckle pattern out. So over the last decade or so, people have developed very advanced techniques to really understand and reconstruct what a complex medium is doing. So a complex medium is characterized by something known as a transmission matrix. In general, a full scattering matrix, but here I'm only talking about the forward transmission part. A lens has a transmission matrix that's fairly simple. A sugar cube can have a transmission matrix that is millions to billions of elements. And these devices that I mentioned previously, spatial light modulators, have really revolutionized our ability to measure a complex transmission matrix. How this is normally done is through the use of a set of probe states that are sent through a complex medium, and then we can measure how this complex medium maps set of probe states I to some set of probe states J, and this is given by these complex valued matrix Tij. I won't go into detail about how this is done, but there's some phase stepping interference involved. And in the end, you'll get some complex valued matrix, which of course I'm not showing complex values here. Once you have the transmission matrix, you can then diagonalize it to find a set of eigenmodes that make it through this channel unscattered. This is equivalent to calculating the inverse of this transmission matrix. And you can do this both before by preparing a set of eigenmodes or undoing the scrambling by detecting a set of eigenmodes. So let's go back to the entangled state for a second. And here I have my 7-dimensional entangled state. I have very strong anti-correlations in the macropixel basis, very strong anti-correlations in my pixel MUB, right? And I can certify using these two sets of data that I have high quality 7-dimensional entanglement. Now, let's see what happens when I send one photon from my state through a multimode fiber. You see immediately that the correlations are completely lost. And at this point, normally we go back to the lab and try to fix the experiment, right? In this case, what we realized, interestingly, was that even though there's no entanglement, this bad data, so to speak, is actually carrying information about the transmission matrix of the fiber. In this case, in the macropixel basis, and in this case, in the macropixel MUB. So this is because of something known as channel state duality, which is a concept which existed for a long time in the realm of quantum information theory. And the concept is quite simple. If you take a maximally entangled state 5+, right, and you send one particle of this state through some channel T, the resulting state rho captures all the information about the channel T. So the statements about the state can be mapped onto statements about the channel and back and forth. This is known as a Choi-Jamilkowski isomorphism, and it was discovered independently by these two mathematicians in the 70s. So the use of entanglement allows us to have an alternate way of measuring the transmission matrix. So here what I'm showing you is that the resulting state phi t is actually proportional to the transmission matrix of the medium, which is given by these elements t, j, I, right? And here what we have is identity operating on one photon T operating on the other photon, and so on, and in that way. Once we have the transmission matrix of the medium, again, we can do the same classical trick that I showed you earlier. We can invert the effects of the medium by calculating the inverse of the transmission matrix and then applying it in some way on the photon that went through the medium. However, with entanglement, we have some interesting options. So operations on a maximally entangled state, on two parties of a maximally entangled state, can be rewritten such that you're only acting on one party or the other. So this is by taking the conjugate transpose and move over the operator B onto the party A, and you can do the same for party B. What this allows us to do is that instead of unscrambling the photon that went to Bob, we can cleverly scramble the photon that went to Alice, and we can still regain our entanglement. So see here, I'm still going through the medium for Bob's photon, but on Alice's photon, I'm doing the inverse transpose, and I get back my state 5+. So this is what we did in the experiment. So here I'm showing you that using the transmission matrix, we can now calculate a special scrambled basis that we measure at Alice. And on Bob's side, we don't do anything. We simply measure as before. And this is my before picture. This is my after picture. So when we measure in the scrambled basis, we get back our correlations between Alice and Bob. Right. So as I've been preaching so far, that in order to certify entanglement, you really need to have correlations in more than one basis. So using some simple maths, we can calculate rotated bases in this complex scattering picture, and this allows us to certify entanglement through this multimode fiber with a fairly high fidelity, so about 84%. Right. We've pushed this result a bit further. Recently in my lab, we've managed to send about 26-dimensional entanglement through again, a commercial multimode fiber that we just buy from Thor Labs. And this is by playing around with the types of measurements we're doing. So this is an example of a hologram where now you see we're using the space a bit more wisely, and these jumps that you're seeing in the gratings are actually the relative phases being moved around. Okay. Right, so this brings me to the last part of my talk, which is on the manipulation of high-dimensional quantum states of light. So you might be familiar with the idea of photonic circuits that is developed, actually, again, somehow Anton keeps popping up in this talk. I know it's not on purpose, but there's an early technique developed by Recht and Zeilinger, which is how do you build a general photonic circuit? And you can do this by constructing it with building blocks made up of phase shifters and beam splitters, Mach-Zehnder interferometers, essentially. And using this method, people have really demonstrated stunning examples of photonic integrated circuits used for everything from natural language processing to entanglement certification. The problem with this is that the number of components you need scales quadratically, and any fabrication errors in these elements again scales up dramatically and creates problems. In addition, you also need control lines for all of these individual elements. So you can see in this work from Dirk Engeland's group, you have individual, I think, thermoelectric phase shifters for each of these phase shifters here, and that tends to be an engineering nightmare. So in my group, we proposed an alternate approach to circuit design, which we call the top-down approach, and this is using inverse design. And the idea is quite simple. We use the natural mode mixing inside a complex medium as a free resource, and we separate our complex media. So the U's are my large ambient mode mixers, and we separate our mode mixers by controlling controllable phase planes P, which we can then program independent of what's happening inside the medium. In this scenario, we are embedding a lower dimensional circuit inside this higher dimensional Hilbert space that is composed of my phase shifters and mode mixers, right? So the circuit T here is d-dimensional, and it's embedded inside this U, which is n-dimensional, and D is much smaller than n. Previously, I talked to you about this 7-dimensional entanglement experiment with my fiber. In truth, the fiber can support a lot more than 7 modes. The fiber we were using was actually could support 200 modes for one polarization. And so in this experiment, then we decided to really use the full modal space of the fiber to try and implement this photonic circuit. I'm going to talk about, in the experiment I'm going to talk about, we implemented a 2-layer circuit. So only one mode mixer, separated by 2 programmable, sandwich between 2 phase planes, which was essentially a multi-mode fiber and 2 SLMs. We explored circuit dimensions up to 7 inside a modal dimension of 200. And in this case, we actually characterized the multi-mode fiber transmission matrix using a new technique that I will not talk about today in the interest of time, but it's basically a very complex optimization algorithm. And this allowed us to figure out what the fiber is doing in this full 200-dimensional modal space. What I will tell you about is the wavefront matching algorithm that we used to program our circuit. So very quickly, here's an example of a circuit I'd like to program, one that does a 3-dimensional discrete Fourier transform. So I want some device that it's essentially a high-dimensional wave plate, right? So it can simultaneously transform from my pixel MUB, which is composed of these modes, simultaneously transform them to my pixel macro pixel basis, so MUB1 to MUB0, right? This is the same as what a half wave plate does, rotation from the DA basis to the HV basis. And these devices don't exist, and this is why this is a big challenge in high-dimensional quantum information. This is how we program our device. We start with so this is all done on a computer. We know what our U's are. We start with random phases at the phase planes, and then we forward propagate our modes of interest, and we backward propagate our output modes of interest and match them at each phase plane using some algorithmic techniques. And we step through this process. So I'll just step through, and you can keep your eyes on over here, and you'll see as I go through, they start converging, and then we repeat this process several times, and eventually, after several iterations, you will find that the forward propagating modes actually then transform adiabatically to the desired output modes of interest. Right. So now that we have this recipe, what we want to do is test it on some high-dimensional quantum states. So we go back to our high-dimensional entangled state right here. On one arm, Alice, we do our standard holographic projective measurements, which consist of a spatial light modulator, single mode fiber that allows me then to scan through any basis of interest. And on Bob's arm, what we're doing is a general transformation. So in this case, we will do a DFT, which will allow me to map from one basis, let's say this basis, onto this pixel basis. And then I can use the fiber array to do a multi-outcome measurement of my modes of interest. So these are examples of gates that we programmed onto using the setup. So the first gate is the identity gate. It doesn't do anything. And this is data in all the mutually unbiased bases of my space. So this is essentially allows us to do quantum process tomography of these high-dimensional gates. And now we also test high-dimensional versions of Pauli gates. So this is a three-dimensional Pauli Z, three-dimensional Pauli X. We do a three-dimensional DFT, and then we also do a completely random unitary transformation. These are density matrices corresponding to these states, and you can see that they seem to match the theoretical matrices quite well. We went up to 7 dim, but as we go to higher and higher dimensions, our fidelities start dropping. And this is primarily because we're just using 2 layers. And I'll speak a little bit more about that in a couple of slides. So why are we interested? I hinted at this earlier. So normally single outcome projected measurements are all we have when dealing with high dimensional transverse quantum states. Having a general unitary transformation will allow us to do multi-outcome measurements using a single mode fiber array or some single photon camera, which are very much in the works right now. So for example, we can use our gates that I showed you, the identity gate and the discrete Fourier gate, as a multi-outcome 2-basis measurement, and then we can apply it to certify entanglement inside the quantum channel itself, inside the multimode fiber. So if I take these 2 data sets, I can use them to apply a witness, a single shot in both cases, and then I can certify that I have a 4-dim entanglement transported as well as certified using the fiber itself. Right, so I mentioned that I discussed the scalability of this technique. So we have 2 options here. One, we can increase the mode mixer dimension, n, or we can increase the number of layers, which of course is a bit harder to do experimentally. And what we showed using numerical simulations was that one can achieve unit fidelities, so almost perfect circuits at low circuit depth, simply by increasing the mode mixer dimension. So for 2 layers, right, if I increase the size of my mode mixer, I start approaching better and better fidelities. Of course, if my circuit dimension is also high, I pay for this at the expense of loss. So success probability is how many photons actually make it through. However, by increasing the number of layers, I can approach unit success probabilities, a 0 loss. So we found that in the regime of the number of layers equal to twice the circuit dimension. So here, for example, for a 4-dimensional circuit, if I have 8 layers, I get unit success probability, so completely lossless design. Right, so that brings me to the summary of my talk today. So first, I showed you how we generate high quality, high dimensional entanglement in the transverse spatial degree of freedom. How we can certify it using a 2-basis witness. I talked about how, well, briefly talked about how high dimensions allow us to tolerate both noise and loss in entanglement distribution. And I talked about how we can transport high dimensional entanglement through a commercial multimode fiber. And then finally, how we can use the same multimode fiber to program high dimensional quantum circuits for light. With that, I'd like to thank my group and my many collaborators who are scattered around Europe. And I encourage you to take a screenshot or photo of this QR code. It'll take you to my website where you can find all of these papers and other information about my group. So thank you very much.
Thank you. Thank you, Mehul. Very nice talk. Bob, are you going to take the questions or should I take them? Let me invite people for questions. Anyone, any question? Either from the Zoom or in the room. But I don't see anyone raising hands here. Let me look at the participant here. So let me ask you a question, Mehul, in the meantime, while people are thinking about it. Everything you do here requires a spatial light modulator, right? I mean, everything you're doing is, I mean, if I understood what you said, you have a different basis. And to go from one base to other bases, you use some kind of spatial light modulator. Is that what the basic idea?
That's so right. So the spatial light modulator is basically a device that allows us to control the phase, the relative phase between different spatial modes. And what it allows us to do is perform measurements or shape light. So basically, it allows us to both prepare and measure photonic spatial modes however we want. So it's really the workhorse for all of the work that we're doing in the spatial degree of freedom. We're also doing experiments with the time degree of freedom. And here, you need the temporal analog of a spatial light modulator eventually.
Okay, and the number of spatial light modulators you need is equal to number of layers you have?
Sorry. So you mean in the last? Yes. Not really. So there. Maybe you've heard of multi-plane light converters, right?
Yes, I've heard that. Yeah.
Right. So you can use the same spatial light modulator multiple times. I mean, there's.
Okay, I see. Okay.
But
Okay.
essentially,
Okay, so there's a question on the chat. Maybe you can look through that on the chat there. There's a question, and you can answer the question directly from there. Or if you want me to read the question, I can read it.
Yeah, I can read it. It's fine. So how do you propagate multiple quantum qubits in your system? The modeling approach. I don't fully understand this question. Can you elaborate, Dan? Are you asking about the theory?
Yeah, I think he's asking theory, modeling approach, yes.
Well, we model things in many different programming languages. I would say, so we have, I mean, there's a lot of work done in Mathematica and in Python, essentially, but it involves, so the transmission matrix, actually, it's an interesting question because there's the physical system of multimode fiber, waveguide, and then there's the abstract approach of just using random matrices, right? Or a matrix approach to understanding how a complex medium works. So normally when we want to simulate stuff, so for example, in this circuit work that I talked about, we're using very simple simulations where we're essentially just using random matrices or structured matrices and seeing what can we do with controlling the phase represented by some vector or diagonal matrix, and then the fiber represented by a random matrix, right? And so that's one approach, and this was, I think, just done in MATLAB. But then the more complex wave simulations are done in Mathematica normally.
Okay, I see. Any other questions here?
Especially here, and now, the people attending in person. Strange concept of attending in person when the speaker isn't here. But for those of you who are attending the talk in person, are there any questions? That's your last chance.
Mehul, I have one more question to ask you. If no one is there, let me ask you my question then in the meantime. So you said that in a multimode fiber, you can actually measure the transmission metrics, how the modes are mixing and mode are interfering. All that information is contained in a matrix form between the input and output sort of mapping. But if the fiber moves or something is changing in the environmentally, something changes, then this matrix actually can change itself. I mean, kind of. So how do you take care of that? I mean, do you just make sure that the fiber, nothing changes? Fiber is very static because the matrix may change.
Yes, indeed. That's a very pertinent question, right? So absolutely, the matrix changes if you bend the fiber. Now, what we found is that the fiber matrix is very, very stable if you just leave the fiber as it is. You can come back even after a week, and the matrix is pretty much the same. You could even pick the fiber up and put it back on the table, and then you get you can focus through a multimode fiber. The focusing returns, so it's very, very resilient. And then there are a lot of people working on ways to model. Well, there's bend-resistant fibers, and then ways to model imperfections inside the fiber, such that you can actually try and overcome any changes that happen, let's say, due to drifts in temperature or even bend losses and things like that. But yes, in principle, we have to make sure our fibers are the same. Right?
Okay. So Usman Javid has a question. Usman, go ahead.
Hi, excellent talk. So I actually have two questions. The first is, so in the last part of your talk, you indicated your propagation of your higher dimensional state through a bunch of unitary matrices. And it kind of smells like a neural And you indicated linear circuitries that have been able to do these kind of things. I was wondering if you had any thoughts about how you would implement nonlinearity, which is an essential component in your unique spatial mode analog of these systems.
Yeah, that's a great question. Filled fibers, that's something that we've been thinking about here. So you don't need the fibers, by the way, right? You can also implement these types of networks on just with free space propagation on the multiplane light controllers. So we're thinking about possibly putting nonlinear crystals in the middle. Of course, the problem is that single photon nonlinearities are not great, right? So this would be more interesting from a classical approach. So yes, so either nonlinear media inside fiber. Again, this is a difficult, well, new field, I would say. Multimode nonlinearities. It's not something that people have really explored. And then or nonlinear, bulk nonlinear crystals in free space.
Okay, I had a second question. So you also discussed about compensating for one photon propagating through a complex media by applying a transformation on the same photon afterwards or the other one. But could you also not consider using the pump power itself while propagating with the generated photons? Because there you have high enough power that you can dynamically look at the behavior of the media and correct for it.
I'm sorry, did you mean use the pump to correct for the to undo the scrambling?
Correct. The pump laser that you would use for an SPDC process, it would continue propagating with the photons through the complex media, and you would have high enough power to maybe dynamically correct for phases that or amplitudes in the complex media instead of using yes. A photon. There's an incredibly low power.
So look, the photon work was more of a proof of concept, playing around, trying something new with which you can do with quantum mechanics. I will not say it's practical, right? But the problem with using the pump is that the wavelength is totally different. It's normally, well, half or thereabouts, right? So the complex medium works very differently with the pump. What we normally do is we'll have another alignment laser that's the same wavelength as the SPDC, and we shape that. So for the circuit work, we use just a classical beam of light. And we got the TM with this intense beam of light very quickly.
Okay, thank you very much.
So Mehul, there's another question in the chart. If you can look at that and answer that, that'd be great.
So Carl asks, can you imagine an optical multimode fiber as a mode mixing medium of an optimal multimode fiber as a mode mixing medium of your system? Yeah, that's another great question. So the optimality here comes down to what is random. You don't want a perfect fiber, because a perfect fiber is basically, you don't get much mixing if you are working in the eigen basis of the fiber. You want some disorder. That's the interesting thing about this idea, that you want mixing. So the basis is with your choice of basis is relevant. You want to work in a basis where you have mode mixing, and you want to work with a medium that has some disorder but not too crazy, such that you lose light or it scatters out. So yeah, that is that's something that I think about, but I haven't quite nailed down what it is. Free space, for instance, free space propagation is good, but light diffracts and you lose light. So waveguides are nice for that.
All right, so last chance for questions. There's a follow-up questions. A couple of questions came up on the chat. You can see that probably, Mehul.
Following up, would extended or localized modes be a good way to look at the optimization? I don't think I fully understand. Maybe we can chat later, Carl.
Good. Can you hear me?
Yes.
So yeah, I was thinking in terms of the bases of the modes of the multi-core fiber, for example. Would it be beneficial for the modes to be localized or extended over the whole profile of the fiber?
Right. Okay. So you're talking about multi-core fibers, which is a little bit different. So in my work, we're just looking at multi-mode fibers where the modes essentially just slosh around. It's just one big waveguide. Multi-core fibers, you want the cores to couple, and this is not normally natural. And so we're exploring photonic lanterns, which are devices that bring multi-core, adiabatically go from multi-core to multi-mode, and in doing so, bring the cores together. So that kind of platform is what is interesting here. Another question is, how about spun MMF or randomly coupled? That's sort of related to what I just talked about. I don't know what spun MMFs are, and I'd be curious to find out what that is. And then finally, we have a question from Pablo saying about the last part of your nice talk, thank you. Using mode mixers instead of beam splitters is a great idea, but are there any losses involved in the transmission between mode mixers? If you use multimode fibers, there are no losses per se, right? They're waveguides, they're fairly lossless. All the light that goes in comes out. Maybe there's some bend loss, a little bit of bend loss, but Govind probably knows a lot more about this than I do.
No, that's correct, yeah.
So, but where it is lossy is the holographic devices that we use. Those are not 100% transmission. There's loss associated with them, but you can have devices that are written, and they can be pretty good in terms of loss.
Okay, so I think that brings us to the end of the talk here. So thank you, Mehul, very, very much. It was a very nice talk. Enjoyed it a lot, learned a lot. So thank you for accepting and coming and presenting. Okay.
Thank you, Govind. My pleasure.
Okay. All right, then. So with that, I call the symposium to come to a close, and again, we can disperse. Okay, bye, everyone.
Bye-bye.
Bye.
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 I'm sorry. When I was his postdoc, he left a lot of his things with us. So he went and recruited his paintings. So I went looking. It's really nice. So for like 3 years I had it's quite impressive. So some people are I could not begin to draw or his mother. He was a military person. Yeah, so usually in the military, you retire when you're like 50 years old. So I think Mayhew's father has Mayhew's father process here. I just don't know with his wife. Thank you for the I'm not worried at all. Yeah, we can. Yeah, I know how to do it.
I'm just not, and.
Usually it's true. I have. Those are going to happen.
I will be there and I may or may not.
But-
Too much.
Oh, yeah. Have higher. There's a. That have the same.
I'll stay away from the.
All
right.
Like, have the same frequency.